I'm sharing actually my desktop. Okay, and go back to the presentation. So, integral formulation. As I told you, this integral reformulation is a way for moving from a PDE problem, partial differential equation problem, to an integral formulation problem. So we are currently moving from this scheme number 2, which is currently this scheme, differential, to an integral 1. Okay? Okay. As a preliminary of application of this formulation, we need to have a dual solution. Consider a special solution of our problem for gradient Laplacian of phi equal to 0. The special solution is the solution, is special in the sense, is a solution with no boundary condition. No boundary condition. But only a mass, fluid mass source concentrated in X star point with unitary mass flow. What does it mean? Mass flux. I have a point. This point is X star, and I have in 3D a mass generation here, and therefore we have something like this. This is a steady solution. It is also known as the special solution, is also known as source solution. Okay? If I take the surface integral of the flux of the velocity in this surface, we have 1 in the sense is 1 mass kilogram per second, which is penetrating through any kind of surface. So we have a special solution. This special solution is written this way. Laplacian of G, this is the name of this solution. The name of special solution, this special solution is G. So G has to satisfy this equation. So the Laplacian of G is equal to, just a second. Do you remember, guy, what is the origin of this equation? The equation written as Laplacian of phi equal to 0, is originally what? The mass conservation. Okay, so note. We have that d rho in dt plus rho divergence of V, excuse me, V divergence, excuse me, plus derivative of rho, excuse me, plus V, the gradient of rho, is equal to 0, right? Okay, and therefore, excuse me.
Sorry, it's rho divergence of D, no?
Excuse me?
It's rho dot product divergence of D.
Yes, I am correcting. I am correcting. Just give me a time. Okay? And this is true if you don't have any mass source here. You have 0 if you don't have mass source. But if you have a mass source in this balance, you have to include some mass source or sink distribution, okay? And therefore, this is 0 for incompressible flow, but here you should have something like a Dirac delta function, okay? So if you divide this by rho, you have, and here you have a Dirac delta function x minus x star. You may imagine in this case of a source of mass in a point, you may have a function as a forcing function of your Laplacian equation. And therefore, in this case, the equation representing this special flow is written in this term. Laplacian of G is equal to Dirac delta function x minus x star, because you are locating a source of mass here in the right hand side, like a concentrated sink of fluid mass per second with the unitary value 1. Okay, so this special problem is true, is a problem with no boundary condition, but the presence of this forcing term in a concentrated point x star is something like an elementary boundary condition, just concentrated in a point. Okay, the interesting thing of this special solution is that this solution is known analytically, is known. You can solve this problem, and the solution, you know the solution, is this. G is equal to -1 on 4 pi oh my god, 4 pi x minus x star in 3D. Okay, so this is the potential, velocity potential of this solution, in the sense that if you consider this scalar quantity and you take the gradient of this scalar quantity in the flow domain, you obtain this velocity distribution around your sink of mass. Okay, the meaning of that 1 on 4 pi in that solution is given by the fact that if you impose that the integral in a closed surface of your velocity induced by g dot n, so the flux in ds, is equal to 0. Since this is the gradient of g, and if you assume this 1 over 4 pi as a generic constant, you realize that this constant has to be equal to -1 of 4 pi necessarily if you want that the flux be 1. Okay, in this sense, this is the source having unitary flux for any kind of surface, including this source point. Okay, you know this solution. This is the source solution, as you know very well. But I want to introduce this solution in a mathematical point of view. The source solution is the solution of the Laplace equation with zero boundary condition, but with the forcing term, which is a direct delta function applied to the x star point, namely the x star point of the location of the source, of the unitary source. Okay, this is the news by you. You know this concept, but I have reproposed this concept, I hope, in a new general perspective for you. Okay, so up to now, I have just included this solution that is the solution of this problem. Solution of Laplacian G is equal to delta x minus x star, no boundary condition. That's it. Okay, but now we have this solution to found phi. Okay, and we know that the Laplacian of phi is 0 plus our complicated boundary condition. Parallelly, we have that the Laplacian of G is equal to delta x minus x star plus no boundary condition. Okay, and now we are going to do, so we have two solutions of the same problem but different boundary condition. Okay, absolutely different boundary condition. Now I want to perform a very standard technique in applied mathematics, the cross product. Cross product means multiply this by G and the other by phi. So multiply this by G and multiply this by phi. Many times you see this in your life. Then consider the difference between these two quantities, and you have G Laplacian of phi minus phi Laplacian of G equal to minus phi by delta x minus x star. Okay, now I want to discuss on this quantity here. My premise is that this quantity can be rewritten in a divergence form. Which means that the following. Look, take the divergence of the product G by gradient of phi. This is a vector operator, the divergence, dot a vector, this vector, and this is equal to the gradient of G dot the gradient of phi plus G Laplacian of phi. How can we demonstrate? Easily by component. When you take the divergence, you are taking the space derivative with respect to an index, and you have this scalar quantity, and you have a gradient of phi, which is the phi on the x with the same index I, because we are taking the divergence here. Okay, so if you develop this derivative, you have the derivative of g with respect to xi plus by the derivative of phi by xi, okay, plus g, the second derivative of phi with respect xi 2 times, and so xi. If you look this by component, by Cartesian component, this is exactly what I've written here. Gradient of g, inner product, scalar product with the gradient of phi, plus g, Laplacian of phi. This is the Laplacian summation on I index. So I have demonstrated this equality, but of course this can be written also inverting the role of g and phi. So phi gradient of g, which is again this term, but here you have phi Laplacian of g. If you consider the difference between these two, you have divergence of g gradient of phi minus phi gradient of g, and this difference, this term is cancelled by subtraction, and here we have g Laplacian of phi minus phi Laplacian of g, which is exactly this quantity here. At the end of this story, I obtain the following. This is equal to, this is equal to the divergence of g gradient of phi minus phi gradient of g, gradient, and this is equal to minus phi delta Dirac x minus x star. This is important. Now we come back to our domain. This is our domain. This is our domain. And we have this relationship to be applied on this domain. And we have the divergence of g gradient of phi minus phi gradient of g equal to phi minus phi delta x minus x star. Note that all these functions are function of x, and x star here is just the location of the source, which is the solution of g. Okay, now this is the domain of our problem V, and this is the volume domain, and this is the boundary of volume domain, which is currently the S domain, which is the union, famous union of U infinite plus S weight plus S body. Okay, and here you have the normal. Now I want to integrate in my domain. Integrate. I have a divergence, is a very attractive divergence form here, and I can take the volume, the volume fluid, dV equal to Again, the integral in the volume fluid in dV. And of course, Gauss is the key name, Gauss theorem. But this is a very special Gauss theorem, because typically in the Gauss theory, what about the convention in Gauss theory for the normal? Do you remember? What is the convention? If you have a closed surface, okay, for applying the Gauss theorem, and you typically suppose the normal to the surface be inward or outward?
Outward.
Okay, so in this case we have inward, right? So we have to put a minus sign here, minus the integral of the closed surface. Look, this minus is for the normal, inward, normal. Okay, and to substitute this divergence with the inner product with the normal dot G, excuse me, G gradient of phi minus phi gradient of G ds. Note the power of Gauss theorem. All the problem is now reduced to the boundary. Yeah, we have a boundary integral, not a volume integral. And you have, indeed, we have the volume integral here in the right hand side. We have a minus sign of the integral on the volume of phi. Phi, remember, phi is a function of x. X and time, of course. But here we have a direct delta function in x star. Okay. So this minus sign can be cancelled. It's a plus sign, please, both sides. And we can perform this inner product. You have n dot G is a scalar, gradient phi is a vector. So after this dot multiplication, we have the integral on the boundary of G d phi dn, which is the normal component of the gradient of phi. Formally is defined like normal derivative, okay? In the normal, it's a gradient in the normal direction. And the minus phi, the gradient of G in the n, ds, equal to, what about this? Do you know the distribution theory fundamental statement, which states that if you have a function of the variable y multiply by the direct delta function placed in y star, and you are integrating in dy, this quantity is equal to f evaluated in y star. Specifically is evaluated where the argument of the direct is equal to 0, and y minus y star is 0 when y is equal to y star. Okay, and therefore here in the right hand side we have the velocity potential evaluated at the point x star. Okay, so this is the elementary integral equation. That's the integral equation. This integral equation is an equation giving a constraint for our unknown variable, but as evaluated in the boundary and in the x star point. Look, in the right hand side, we have our solution evaluated in a x star point, which is an arbitrary point. which is the arbitrary point where I'm locating. I can imagine this point as a point where I locate a source if I have in mind G. But now G is a closed fact. G is closed because we know G. G for us is a function with a special characteristic to satisfy the Laplace equation. But we can forget the physical meaning of G. We don't need at the moment. I can associate to G a role for X and X star because I know that, I remember that G, where is it? G is -1 on 4 pi modulus of X minus X star. So G is effectively a function of X and X star, of course. And so in the right-hand side, I have the velocity potential evaluating the point X. And in the left-hand side, I have an integral, pay attention, to be performed in the X variable. So whenever you have performed this integral, at the end, you have a function of X star as well in the left-hand side. Okay, so this is consistent. You have a function of X star in the left-hand side, a function of X star in the right-hand side. Okay, and my solution is phi, and my solution has to satisfy this. Period. But please do not forget the special point that this S is S body plus S infinite plus S wake, because this is my boundary. I have a complicated boundary at infinitive, on the way, on the body, and on the wake. I have this tribal vision for my boundary. I have this, I have this, and I have this. Okay, and therefore, please decompose this integral in the domain. Since the domain is the union of three domains, this integral should be the integral on the surface S infinite of the argument plus the integral of S body, the same argument, plus the integral on the, please, if I use this circlet, I have to consider SW prime and then take the limit. I shall illustrate to you these three S infinite, S body, S wake in domain, and this is equal to phi on the X star. Okay, look, S infinite is something starting here, and then let me use the color to be clear, red color, and so I have this infinite and close here, tack. So I have a closed envelope, closed red envelope for S infinite. What about S body? Another envelope, a yellow envelope, and I have this envelope here and close here at the trailing edge. And then another color, green, I have another envelope for S wake prime, please, at the beginning is something like this. It's another envelope, a green envelope for S wake prime. And then I have to take the limit for S prime having zero thickness, so becoming S wake at all. And for all this transition, this closed integral will become an open integral without the circle, but on the S wake surface. Okay, but let me show this development in deep here. the next slide. Let me consider this again. And so I have that S, what is the color? Red. S at infinity of G d phi dn minus phi dg dn ds. Okay, so in the red surface here, what about the boundary condition? We have that phi is 0. Here, phi is 0. And also the phi on the n, which is the normal velocity at infinite here, is 0 as well, unperturbed flow at infinite. So this integral contribution is 0. Okay? As concerning the yellow integral on the body, I have this body and we have to keep all the term, of course, in this integral. But remember that this term here is identical to v body dot n. So this is the body boundary condition. This is also known as wall boundary condition, wall body boundary condition. This is the input of my problem, the motion of the aircraft. This is the input of my problem. Okay. Okay, this is the yellow integral. So go to the last integral, the green one on the wake. This integral at the beginning is something like closed integral on the S wake prime surface. Okay, and here I have G d phi dn minus phi dg dn in the S, and we have this integral can be decomposed in two integral in two contribution. One on the upper part here. Look in the what is it? In the upper part here, and another one in the lower part. I have this is the look. I have this surface which is approaching the wake surface. This surface is the S wake prime surface. I have a 1 value upper and a 2 value lower. Here I have this normal, and here I have this normal in 1. Okay, and so, for example, in this term here, I have something upper and and correspondingly something lower. But these two normal are opposite. Okay, and so you can express one as minus the other. So you can use the same normal and cancel this and put a minus sign here. And so you have the phi on the n upper minus the phi on the n lower, but this is 0 for the fact that delta Vn is 0, delta d phi dn is 0. I am applying the wake boundary condition. And so this term, tra, is 0. So when you take the limit of s wake prime going to s wake, this integral should become an integral on the wake surface. Note, I don't use the circle because now this, look at my hand, this double enveloping surface s wake 1 are collapsed to a unique discontinuity surface up, and this is s wake at the limit. So, and this is a just open surface s wake, okay? And we have minus sign, and this phi is phi upper and phi lower because of this normal, which is opposite upper and lower. And so we have delta phi. Oh, welcome delta phi, welcome. Delta phi dg dn ds. Final equation, drumming. We have an integral on body surface of g d phi dn minus phi dg dn on the body, which was the old red the old yellow integral. The red integral is cancelled, and the green integral, we have only minus the integral on the wake, delta phi dg on the n. This quantity has to be equal to the value of the potential in the x star point. And ladies and gentlemen, this is the final boundary integral equation for the velocity potential, which is alternate or alternative to the differential problem. Note that we have only integral on the body and on the wake only. And if you imagine to discretize this equation for finding your final value for phi, you have just to consider as domain the body surface domain and the wake surface domain, and that's it. This is the main advantage of this kind of formulation. So I think that we can stop here, because what we have find is a very, very important result for our unsteady potential flow formulation. By this result, we will obtain our aerodynamic operator for the aeroelasticity. Okay? And this is the basic mathematical physical concept for describing potential, unsteady potential flow, and for characterizing the dynamics over the aerodynamics. This is not a joke or a word play, but is just an emphasization of the concept that also the aerodynamic has an internal dynamics. Okay, and the internal dynamics of the aerodynamic is represented by this equation, when we have wake and delta phi mechanism, convection mechanism, together with the other facts related to the potential flow. Note that we have used all the equation, we have used all the equation of the differential problem, we have used this, look, we have used this, we have used this, we have used this, we have used this, but we have not already used this, the last one. So we have just to play this last card for complete our description. Okay, so thank you for your attention. I have take the opportunity to have your fresh brain early in the morning, so I have pushed my accelerator in my machine, but I think that you were ready for following me. I hope so. And so we will meet again in the afternoon at 2 o'clock. Thank you for all.
Please, Professor, just 1 minute. I have a question about when we include the solution of G for G. So we thanks to the linearity of the Laplacian, we can include the solution for the source. So when we make the difference between...
Look, G is a absolutely known function, and also the G on the end can be analytically evaluated. So this is known. This is known. And this is known from the unsteady boundary condition by the body motion, okay? The only unknown here is this phi here. And the other unknown here is this phi here, okay? And of course, phi on the wake, so having the delta phi. So everything is known, but the unknown are here underlined in green. So this is unknown. This is unknown. And this is unknown. And next, in the afternoon, I will show you how to find this unknown by a numerical approach.
Okay, thank you.
Okay?
Scusi prof, una cosa, ma l'integrale su S-Wake non era più chiuso, aveva detto?
Questo qui è aperto, qui è S-Wake, non è S-Wake primo.
Sotto, alla fine, dico. L'ultima equazione, quella che ha in rosso, qua.
In rosso?
È l'equazione
che ho sottolineato?
È l'ultima proprio, l'ultima della slide.
C'è scritto S-Wake, no S-Wake primo, è S-Wake. Ah, sì, ho capito.
Quindi... Okay.
Sì. E non lo posso cancellare adesso perché sono rientrato, va bene, lo cancello così. Ok?
Perfetto, sì.
Ok?
Grazie.